Hey there, my name's Lukas and I'm a physics student here at Northeastern. Today we're going to be doing a really cool experiment where I drop this neodymium magnet down this aluminum pipe. Now as you know, aluminum is non-magnetic, unlike some other metals such as iron, so the magnet isn't attracted to it. Similarly, the magnet is not attracted to the cardboard in this tube. So as you can imagine, nothing very special is going to happen when I drop this magnet down the tube. See? The magnet is in free fall as it's traveling through this cardboard tube. But what will happen if I drop the magnet down the aluminum pipe? You can clearly see that the magnet is not traveling as fast through the pipe as it did through the tube. Let me show you an aerial view so you can actually see what's going on as I drop it. You can see as the magnet's falling through that it's not actually accelerating like it would in free fall, but rather it's moving at some constant velocity. Now this is pretty cool, but what's actually causing it? To answer that question, let's look at a simpler example. Instead of a long pipe, let's take a single conducting loop. Imagine a magnet such as the one I've drawn here moving towards that loop. The motion of the magnet causes the magnetic flux through the loop to change, and that change in flux induces an EMF onto the loop. This phenomenon, known as magnetic induction, is actually how we generate most of our electricity today. Let me show you. Here we have an oscilloscope connected to a loop like the one I've drawn. On the screen of the oscilloscope, you can see voltage as a function of time. Notice how when the magnet is motionless, the voltage is 0. But if I move the magnet, you can see the induced EMF. Also take note of the velocity dependence of this EMF. If I move it through slowly, there's not much of a change. But if I pull it through quickly, you can see the big spikes. Additionally, I don't actually have to move the magnet to induce an EMF. Moving the ring will produce the same effect. Or I can rotate the ring. The flux is still changing through the loop, so this is still inducing an EMF. Since this is a conducting loop, there's also an induced current on the loop. This induced current generates its own magnetic field, and from Lenz's law, we know that this induced magnetic field will point in a direction that opposes the change in flux through the loop. In our example, the magnet is pointing and moving downward toward the loop, so the downward flux will be increasing. This means that the induced field will point upward to oppose the change in flux. This is like putting the north poles of two magnets together. Through this induced magnetic field, the ring is applying an upward force on the permanent magnet by pushing on it. Now let's consider the case where the magnet is still pointing downward, but is moving away from the loop. Since the magnet is moving away, the flux is now decreasing, and from Lenz's law, the induced magnetic field will now point downward to oppose the decrease. This is like putting the south pole of one magnet to the north pole of another. The ring is actually still applying an upward force on the magnet, but this time by pulling on it. We can think of the pipe as a stack of these rings, each one applying its own upward force on the magnet. The total force will be the sum of the contributions of each ring, and since the force is dependent on the EMF, it is proportional to the velocity of the magnet. As the magnet moves faster and faster, the force will continue to increase until it equals the force of gravity acting on the magnet. This is why the magnet appeared to be moving at a constant or terminal velocity. In a moment, I will show you how to calculate this terminal velocity in terms of the properties of the pipe and the magnet. Here we have our magnet falling through the pipe. We want to find the force that the pipe exerts on the magnet, but this is a pretty difficult place to start. We could, instead, look at the example I showed you a moment ago with the magnet falling through a ring, but even this is too complicated as we don't know the expression for the magnetic field of our magnet. Instead, we're going to assume that our magnet is small compared to the pipe and therefore can be approximated as a magnetic dipole. We can find the force that the ring exerts on the dipole, and summing the forces for each ring will allow us to determine the force that the pipe exerts. This is a pretty straightforward calculation, but it actually gets really lengthy, so we're going to break it up into parts for you. First, we'll look at the magnetic field of a dipole, and then using Faraday's law, we can determine what the induced EMF is. Using this induced EMF, we can calculate the force that an individual ring exerts on our magnet, and summing over the dimensions of the pipe, we'll find the force that the entire pipe exerts. Lastly, using this force equation, we'll write the equation of motion of the magnet, and solving the equation, we'll actually be able to determine the time dependence of the velocity and find the terminal velocity. Let's begin. Here we have the expression for the magnetic field of our magnetic dipole. I'm not going to show you how to find this today, but Google is your friend. You can see this m term in the expression, and it's known as the magnetic moment of the magnetic dipole, and it represents the strength and direction of it. Here, we've chosen m to be in the z direction, so that it's equal to mz hat. Additionally, this m dot r term that you see just becomes equal to mz, since z hat dot r is just equal to z. We want to find the x, y, and z components of our magnetic field, and to do that, we take the dot product of our b vector and the x hat, y hat, and z hat components. For the x component, you can see the mz that comes from the m dot r, as well as an x term that comes from x hat dot r. The m over r cubed term drops off because m is perpendicular to the x-axis. The same is true for the y term, but this time, instead of x, we have a y. Lastly, for the z component, you can see the m and z that come from m dot r, as well as an additional z that comes from z hat dot r. This time, the second term does not drop off, but just becomes 1 over r cubed, since z hat dot z hat is just equal to 1. So now we have our x, y, and z components of the field, but since our field and pipe are cylindrically symmetric, it's actually more useful to use cylindrical coordinates. In cylindrical coordinates, we maintain this z component, but instead of x and y, we now have a vector rho, which is perpendicular to the z-axis, and phi, which determines the angular direction. I'm sure you've seen r to be equal to the square root of x squared plus y squared plus z squared, and here in cylindrical coordinates, it's actually just equal to the square root of rho squared plus z squared. Now in this system, our b vector becomes equal to b rho rho hat plus bz z hat plus b phi phi hat. But since we have cylindrical symmetry, this term actually is 0. We already know what the z component is from earlier, so we just have to calculate b rho. Just like rho is equal to the square root of x squared plus y squared, b rho is actually just equal to the square root of bx squared plus by squared. Plugging in the expressions that we found earlier for these two values, we get that b rho is equal to mu naught m over 4 pi times 3 z rho over rho squared plus z squared to the 5/2. Now that we have b rho and bz, we can finally get to calculating that EMF I kept rambling on about earlier, and we're going to do so using Faraday's law. Faraday's law can actually be written two different ways. The first is as the negative time derivative of the magnetic flux, and the second is a more general equation, and it's the integral of v cross b dot dl. I'm going to show you how to use both of these equations to find the EMF, and you're going to see that the second one is far easier to use in this example. But first, let's calculate the magnetic flux. The magnetic flux, phi, is equal to the integral of B dot dA. Here, you can see the magnet fixed on the origin and pointed in the z direction. The ring is perpendicular to the z-axis and is located some distance z away from the origin. And for simplicity's sake, we're going to choose the vector dA to be pointed in the positive z direction. This means that the dot product B dot dA becomes BZ dA. We're going to model dA as this ring with radius rho and thickness d rho, so that dA becomes equal to 2 pi rho d rho, and we'll integrate this expression from 0 to r. Plugging in BZ, we get this fairly complicated looking integral. But we can make it a lot simpler just by doing one substitution. If we set u equal to rho squared plus z squared, du becomes equal to 2 rho d rho. And our limits now are z squared and r squared plus z squared. Substituting these values in, we get a much easier integral of two power functions. After integrating and doing a little bit of algebra, we get that the flux is equal to mu naught m over 2 r squared over r squared plus z squared to the 3/2. In this equation, you can also see that when z equals 0, or the ring and the magnet are on the same plane, that the flux is maximized. Now that we have the flux, we can find the EMF. We know that the EMF is equal to the negative time derivative of the flux, but using chain rule, we can rewrite this as negative d phi dz times dz dt. dz dt is actually just the velocity, so we get that EMF is equal to negative d phi dz times v. If we plug in the flux that we just calculated and take the derivative, we get that the EMF is equal to 3 mu naught m over 2 times r squared z over r squared plus z squared to the 5/2 all times v. Now I'm going to show you how to use the second equation, the integral of v cross b dot dl. Since the velocity is in the z direction, v is equal to v times z hat. We already know that b is equal to b rho rho hat plus bz z hat. And when we take the cross product of these two vectors, the z components go away, and rho cross z is equal to phi hat. So we get that v cross b is equal to v b rho phi hat. Additionally, dl is equal to r times d phi phi hat. If we add these values in and integrate from 0 to 2 pi, we get the same exact expression as before. And you can also see that this method was far easier to use. Additionally, you can see from the equation the proportionality of v that I was mentioning earlier. Also, if I plot this equation, you can see that it's very similar to the plot that you saw on the screen of the oscilloscope. What this means is that our approximation is actually pretty accurate. Now that we have expressions for the magnetic field and the EMF, we're ready to calculate the force. For simplicity, we're going to fix the magnet on the origin and point it in the positive z direction. The ring is moving with some velocity v in the z direction. Now from Newton's third law, we know that the force exerted on the magnet due to the ring is the opposite of the force exerted on the ring due to the magnet. Additionally, the cylindrical symmetry of our problem means that the net force is in the z direction. What this means is that the force is equal to the negative integral of I times dl cross b sub z. dl is in the angular direction, so the cross product of it and b is b rho dl. And dl is equal to r d phi, so when we integrate from 0 to 2 pi, we get that the force is equal to 2 pi ri b rho, where I is the induced current on the ring. We know what b rho is, but we have to find what this induced current is equal to. From Ohm's law, we know that the voltage is equal to the current times the resistance, and solving for the current, we get that I is equal to V over R. Or we can rewrite this as I is equal to VC, where C is the conductance and the inverse of the resistance. This C is also equal to sigma times A divided by L, where sigma is the conductivity of the material, A is its cross-sectional area, and L is the length. What we want to do is find the total force acting on the magnet due to the pipe. We're going to do this by dividing the pipe into infinitesimally thin rings that each exert their own infinitesimally small element of force, dF. Now each ring is infinitesimally thin, so they have this cross-sectional area of dA. If we substitute our I expression in, we get that dF is equal to B rho times the EMF times sigma dA. Now we can plug in our expressions for the magnetic field and the EMF and get the following expression for the force acting on the magnet due to a single ring. Now to find the total force, we have to integrate this over the dimensions of the pipe. For R, we're going to integrate from A, the inner radius, to B, the outer radius. And for simplicity, we're going to assume that the pipe is infinitely long and integrate Z from negative infinity to infinity. Now, this is a much more difficult integral than before, so it's going to take a few tricks. First, we're going to start by integrating over the Z variable. And the first step to that is doing what's called a trigonometric substitution. I'm going to set Z equal to R times the tangent of theta, which means that dz is equal to R times secant squared theta d theta, and R squared plus Z squared becomes R squared secant squared theta. Our limits become negative pi over 2 and pi over 2. If I substitute these values in and do a little bit of algebra, I get that the expression is equal to 1 over R to the 7th times the integral of cosine to the 6th theta minus cosine to the 8th theta. Now this looks pretty simple, but this is actually a very complicated integral due to the high powers. So instead, I'm going to do another trick. What I'm going to do is I'm going to define the function f2n as equal to the integral from negative pi over 2 to pi over 2 of cosine to the 2n theta d theta. If I use this definition, our expression becomes 1 over r to the 7th times f6 minus f8. Now, what I'm going to do is I'm going to take my definition and use integration by parts to find a recurrence relation that'll lead to a general expression for our definition, and it will allow us to solve for any n value. As a reminder, integration by parts states that the integral of uv is equal to, u dv is equal to uv minus the integral of v du. Here, we're going to say that u is equal to cosine 2n minus 1 theta, and that dv is equal to cosine theta d theta. You can see that this first term is actually going to go to 0 when we evaluate at the limits, and after a little bit of algebra, we get that this integral is the same as 2n minus 1 times the integral of cosine to the 2n minus 2 theta minus 2n cosine to the 2n theta d theta. Now if I use our definition, this simplifies to 2n minus 1 times f2n minus 2 minus 2n f2n. You can see that we have our definition on both sides of the equal sign. What we can do is solve for it and get that f2n is equal to 2n minus 1 over 2n times f2n minus 2. This is a recurrence relation because we have f2n in terms of the previous term f2n minus 2. And we can continue to iterate this so that we have f2n in terms of f2n minus 4 all the way down to f0. And f0 is pretty easy. It's just the integral of d theta evaluated from negative pi over 2 to pi over 2. This is just pi. We can also simplify these coefficients down to a general term and get that f2n is equal to 2n factorial divided by 2 to the n factorial squared all times pi. We can then use this to find what f6 minus f8 is and get that it's equal to 5 pi over 128. If we substitute this value in and then integrate over r, we finally get that the force exerted on the magnet due to the pipe is equal to 15 over 1024 times mu naught squared m squared sigma times 1 over a cubed minus 1 over b cubed times the velocity. So we found the equation for the magnetic force acting on the magnet. You can see it's in terms of things like the dipole moment, the conductivity of the pipe, the dimensions of the pipe, the velocity of the magnet as it falls. But all of these terms except the velocity are constant in our experiment, so what I'm going to do is I'm going to group them all together as a single value k. Now what I want to show you is the equation of motion of the magnet as it falls through the pipe. Here in this free body diagram, I've pointed the positive z direction downward for simplicity, and you can see the force, the magnetic force, and the gravitational force acting in opposition to each other. Now the net force is equal to mg minus f, and from Newton's second law, we know that this is equal to the mass times the acceleration. The acceleration is just the time derivative of the velocity, so I can also rewrite this as m dv dt equals mg minus kv. If I divide both sides by k, I get m over k dv dt equals mg over k minus v. Earlier, I mentioned terminal velocity and that it was achieved when the magnetic force is equal to the gravitational force. When this happens, the net force is equal to 0, and so is the acceleration. When this acceleration is equal to 0, you can see that the terminal velocity is equal to mg over k. I'm also going to define this time constant, tau, as equal to m over k. You'll see the meaning of this in a moment. But first, I'm going to get this equation in terms of tau and Vt. Now this is what's called a differential equation, and you don't need to know much about them right now in order to solve this. What I'm going to do is get like terms on the same side and then integrate from 0 to v and 0 to t. If I do this, I get that the negative natural log of Vt minus v over Vt is equal to t over tau. If I exponentiate both sides and then solve for v, I get that the velocity of the magnet is equal to the terminal velocity times 1 minus e to the negative t over tau. Here in the plot of the equation, you can see that when t is equal to 0, this exponential term is equal to 1, and the velocity is equal to 0, like expected. You can also see that when t is equal to infinity, the exponential term becomes 0, and the velocity becomes the terminal velocity. You can also see the importance of this time constant tau, as it determines how quickly the velocity approaches the terminal velocity. After just one time constant, it's at 63% of the terminal velocity. After 2, it's 86%. After 3, it's at 95%, and 4, it's 98%. So it only takes a few time constants to get practically at the terminal velocity. In our experiment, we can assume that the time constant must be very small because the magnet appears to achieve its terminal velocity very, very quickly. So that's all I have for you guys today. As I promised, there's the time dependence of the velocity and the equation of the magnetic force acting on the magnet. In the next video, we're going to put this equation to the test and change the dimensions of the pipe and the materials of the pipe. So be on the lookout for that and a few more exciting videos. Thanks, guys.